Welcome to micro communication course. Today we continue here the measurement of a Q of a cavity here. So in earlier method we say that a transmission method we supposed to find out the Q of a cavity. In that case we need to draw a graph of a power with respect to a frequency there. So in this case we'll get a graph that is about a inverted U, and that inverted U wherever we get the maximum power, this one is about a maximum value of a power. So when we'll get the maximum power? At the resonating frequency of a Q. From this, we are supposed to find out a 3 dB point, a half power point, so that we'll get that F1 and a F2. And through that F1 and F2, we calculate the bandwidth, okay, so that we are able to calculate the Q of a cavity. So what is the Q of a cavity? Q of a cavity is nothing but what? Resonating frequency with respect to the bandwidth. So we'll get a Q of a cavity. That is about a through a transmission method. Then second method, that is about a VSWR method. The same setup is there. Okay, and that plotted section is earlier it is connected to the power meter, and then we need to vary the frequency of a signal there and measure the power. At a resonating frequency, we'll get the maximum power, and then from the maximum power we calculate the Q of a cavity. So here Q is nothing but resonating frequency and bandwidth, that is about these are the two half power points. Okay. Next about the VSWR. So in a VSWR method here, so in that case, plotted section is connected to the a power VSWR meter. Okay. So, we need to measure that uh, a VSWR of a uh, your signal there. Okay, because the cavity is we have the cavity, whatever the setup we supposed to consider that. This one is about a cavity. Cavity is connected to the slotted section with probe carriage or a standing wave detector. And then this standing wave detector is to be given to the VSWR meter. Okay, this one is the body meter. And then a VSWR meter, okay, we need to calculate the a VSWR meter with respect to a frequency. We need to draw a graph with respect to a VSWR and a frequency. Instead of a power, we supposed to consider the VSWR with respect to a frequency there. So now that graph is looks like here. We consider that this one is about a frequency. Okay, here we have a frequency, and this one is about a VSWR. When we propagate any signal through the device, that is through the cavity there, with a different frequency, variation in the frequency. So in that case, at a resonating frequency, your VSWR will be very, very low. So suppose here we say that at a resonating frequency, we'll get the very, very low resonating frequency. Means a resonant frequency at which the VSWR is the lowest, and from this lowest frequency, we supposed to note down, okay, what will be the VSWR. Okay, what will be the minimum VSWR at the resonating frequency. And then from this, whatever the lowest value of a VSWR here, so we need to find a half power point to this VSWR. So how to find out the half power point? So again, we supposed to consider that a graph. Here we are getting the VSWR there. So then we supposed to find out a 3 dB point, or we can say that a half power point. So that we'll get that a F1 and a F2 here. So again, same formula we can calculate here FR by the bandwidth here. Okay, so that is about what you can say that a measurement of a Q of a cavity through the VSWR a method here. Okay, so next we see that another measurement topic, that is about a measurement of a attenuation there. Okay, Now this one is about a measurement of a attenuation. Now in the case of a measurement of attenuation, it is just like a how much is the power is attenuated by the device under test. Okay, or we can say that in between a microwave bench, we supposed to insert a device there, and because of insertion of a device, how much will be the attenuation takes place because of that insertion of the device in a set of them. So that is to be measured here. Okay, so that is in the form of what we can say the attenuation. So there are the two types of a attenuation measurement. Okay, so one is about a power ratio method here, and another is about a substitution method. Okay, so we consider that one is about a power ratio method, and then next next we supposed to consider that a RF substitution method. Okay, so we start here first with a power ratio method, and then we see that a RF substitution method. Okay, so now in this case of a power ratio method, we supposed to measure that a power when we insert the device. Okay, so for a given particular device, when we insert the given device, then what will happen to the uh, attenuation there? Okay, so now we see that a source supply. Okay, then we have a given particular source there. That source may be your reflex liston, gun diode, then isolator. Okay, then we have the attenuator here. We see that a attenuator there. Then after that, we're supposed to consider that a device under test. And then after that, use standing wave detector. Okay, this one is about a standing wave detector. And then standing wave detector is connected to the matched load. Okay, so this one is connected to the match. And here a power meter or a power indicator. Okay, so now this one we consider that main block here. So whatever the source supply, if it is a klystron power supply, then a klystron source, then your isolator. It is used to isolate the source and the load here. Attenuator, that is for your how much is the signal is to be propagating through that through it. So then a device under test. And here the device under test is useful for measurement of attenuation. So when we place a device here, so what will be the attenuation takes place? Okay, so that is a device under test for which a attenuation is to be measured there. So that's why that device under test is to be placed before the slotted section of the microwave bench or the standing wave detector. And this slotted section is connected to the match load here. Okay, one load, but it is terminated with a match load. And again, for this particular slotted section, there is a tunable probe. Okay, on this standing wave detector, there is tunable probe, and that tunable probe is connected to the a power meter. This one is about a power emitter or a power indicator. Now, in this case here, so power meter is used to measure that what will be the power when we insert a device under test here. So to measure the attenuation there, we supposed to measure the power when we have the device under test is inserted in this particular microbench with insertion and without insertion. Okay, we need to measure that a power meter P1 and a P2 value with DUT and without DUT. Okay, suppose we consider that a power P1 that is with device under test and P2 that is without device under test. Okay, now device under test means what? So now here, so any component when we insert in the given microwave page, so because of that component insertion in the microwave page, so what will be the attenuation occur? For that purpose, we supposed to measure that a power at a power meter with device under test and without device under test. So then we can measure the attenuation. So attenuation of the given particular device under test is equal to A is equal to 10 log of P2 by P1. So that we'll get the attenuation. Okay. So in the case of a power meter here, so directly we will get that how much is the power measured without device under test and with the device under test. So directly we'll get the a power there. But there are some drawbacks of this power ratio method measurement here because when we consider a micro bench there, okay, so there will be some shortfall at the device here. Again, there will be some shortfall at this a power meter there. So because of that, there will be error. So it is not the accurate power ratio attenuation measurement. Okay, this is not a accurate measurement of the attenuation there. Then another method is about a RF substitution method. Okay, so next method we say that the RF substitution method. One is the second one, RF substitution method. Okay. Now in the case of a RF substitution method here, we supposed to measure that we supposed to eliminate the whatever the inaccuracy occur in the given device. Okay, so that's why a RF substitution method is designed here. But here everything is the same here. Okay, so we have a that bench for our setup for the measurement of the attenuation using the RF substitution method. Everything is the same here. Okay, so here we are supposed to consider that a source. We supposed to consider source supply, a source isolator attenuator, then a device under test, standing wave detector, power meter, match. Only one change is there. What is the one change? So there is a device under test, as well as we supposed to consider that one more component. That component is called as a attenuator. Okay, this one is about a variable attenuator. So now in this case of, or we can say that a precision attenuator. Okay, we can say that here. Okay, now in this case we supposed to consider that variable precision attenuator. Okay, variable precision attenuator. Now in the case of a micro measurement, that is about a attenuation measurement here, we supposed to consider that a variable precision attenuator here. Now what happen here? When we the setup is same, we supposed to consider that source, reflex piston, power supply, reflex piston here, then isolator, then attenuator, all the components we have seen. Now in this case here, so initially we supposed to consider that a device under test to be inserted here. Okay, we supposed to use a device under test here and measure that what will be the a power there. Okay, so that is about a power meter. Using the power meter, how much is the power we supposed to measure? Everything is the same. No changes occur. Now then replace the device under test with a variable alternator. Okay, this one is about a variable alternator here. Then here we supposed to measure some power here. For example, some x value. Because when we insert the device under test, we'll get some x values there. Then we remove that device under test and then put the alternator here. When we put the alternator here, then what happen here? Then we need to vary the alternation in such a way that we will get the same x value at this particular power meter. Okay, and then at this particular value of the alternation here, because we are varying the alternation here, so that we'll get the same x value, that value we got earlier with a device under test, so that by adjusting the alternation value, so that we'll get a same x power value at this particular meter here, so that we'll get directly the alternation. Okay, so how much is the alternation? That directly noted by this alternator. Okay, that device here. So direct method of a alternation here. On here, RF substitution method is what? We just replace a device under test. Initially, we need to measure the power using a device under test, that is process 1. Then remove the device under test, that is whatever the device under test we have here. Replace that device under test with a alternator. That alternator is what? Variable precision alternator. And we need to adjust the power using the variable alternator there. So instead of a power meter, some people can use a VSWR meter here. So using a while inserting the device under test, we're supposed to get some VSWR value, that is about a meter point indicating some VSWR point here. Then we replace that device under test and put that alternator. Then vary the alternator here, okay, and then find out the point where we got the deflection earlier through the device under test until that particular point reaches through the variation in the attenuation. So once that point reaches, so then directly we'll measure the attenuation there. So that's all about what we can say, that a measurement of a attenuation. Next, we consider that another method of a measurement of attenuation here. So these are about the measurement of attenuation. Okay, so another measurement topic we consider here, a measurement of a frequency there. Okay, next topic we consider that a measurement of a frequency. This one is about a measurement of a frequency. Now, to measure the frequency, there are the two types of a measurement here. One is about a deep method. Okay, so that in that case we supposed to use a wave meter there directly, and then we can measure that a frequency there. So one is about, we can say that, a deep method, and another one is about a slotted line method. There are the two types of a frequency measurement. Okay, so that is about a frequency measurement means what? A micro frequency measurement. Now, in this case here, we consider that in a deep method, first case is about a deep method. So then we will see that what will be the frequency using a slotted line method. So one is about a deep method. So in a deep method, we supposed to use a wave meter. Okay, in a deep method, we use a wave meter. So what is the wave meter? Wave meter, as we have seen earlier, here we supposed to consider that a rectangular waveguide, and here for this rectangular waveguide is small cavity is there. Okay, and here we consider that a small plunger Okay, this one is about a plunger here, and then we supposed to rotate that particular plunger here. Okay, when we rotate that plunger, then a cavity. This one is about a RF signal. F in will get that a F out, RF out. Okay, so that Fs, we say that RF in, it has a signal frequency Fs here, and here is about a RF out. Okay, so now for the given particular cavity, it has some resonating frequency. Okay, so now this one is about a cavity. So through the plunger, if we're supposed to be rotate the wave meter in a given direction, whether it is the clockwise or anti-clockwise. So according to that, we need to adjust the resonating frequency. Okay, the outer means we supposed to propagate a signal through the wave meter here. This one is about wave meter. It has a wave guide here. Signal is still propagating through it. Then we'll get the same signal here out. But if we rotate this wave meter, so at some particular point, the signal frequency and the resonating frequency of the device match. Because when we are rotating, means that plunger will move up and down. And because of moving up and down, the cavity size changes. If the cavity size changes, the resonating frequency of a cavity changes. Now we measure that what will be the point where we are getting that Fs is equal to Fr. Okay. So when that resonating frequency and signal frequency match, then output will be degrade. It will be zero because a standing wave occur. And because of that standing wave occur, so output across this particular guide will be a zero. So that's why we can say that it is about a deep method. Okay. So if you consider that output measure on a CRO or if you use a VSWR there, then that pointer will be deflect to the deep here, or if you measure on a CRO there, whatever the signal, this one is about a RF signal that is modulated one. Suppose modulating at 1 kilowatt now. So in that case, what happened? Initially, we supposed to see that this one is about a modulating signal. Okay, this one is about a signal now. So when we say that Fs is equal to Fr, so in that case, we will see that just like a small block. So your signal gate, what you can say that a deep occur. So this deep occur because of that Fs is equal to Fr. Because of that deep occur, so at that particular deep, so on the wave meter directly we can measure that what will be the frequency there. Okay, that is about a deep method. Then there is a scale on the wave meter. There are the two rings. In between that two ring, one scale is there, and that two rings are coinciding that particular scale. Okay, so just like I supposed to say that this one is about a scale now. So it has a scale likewise. If you see that wave meter, so this one is about a likewise different scales are there. Okay, so these are about the scale. Okay, so different scales are there. So we can say that it has a different frequency. Suppose I am saying that it is about 8 gigahertz, then 9 gigahertz, 10 gigahertz, 12 gigahertz. Likewise. And here we can say that one line is there, one vertical line is there. And in between that vertical line, two lines are there. Okay, these two are fixed. They are rotating. When we are rotating, so it will be rotating from one scale to the another scale. Okay, when it go up or down, so it will be just rotating with a different scale. So this vertical line and this green line, it will coincide at one particular scale here. So this one is about a scale here. So at that particular point, so that will be the frequency. Okay, so direct method, that is about a deep method. So on a wave meter, there are a two lines. Okay, if you see that on a wave meter, if you consider here on a wave meter, these are the two lines are there, and that two lines, in between that two line, one line is there, vertical line is there, and that vertical line is used to measure the what will be the frequencies. Okay, that's through the wave meter. Okay, that is called as a deep method. Okay, next is about a slotted line method. Another case here is slotted line method. Now, in the case of a slotted line method, so we have a same setup here. Okay, we consider that the setup is same now. We say that a source supply. Okay, then we supposed to consider that a given source now. Then after that, we have a isolator. Okay, isolator. Okay, then we have a flap alternator. Okay, this one is about the alternator. Then we supposed to consider that a frequency meter. Oh, that is a wave meter. Okay, we say here because wave is propagating through it. And then a standing wave detector. Standing wave, that is SWD. Okay, standing wave detector. And after that, we supposed to consider that here VSWR meter. And then we supposed to connect, okay, because on a tunable probe, then we supposed to use a short. Okay, this one is about a short. So in this case, a slotted line method here, we need to use a cutoff wavelength and a guide wavelength to calculate that a free space wavelength here. So we should know that what is the equation of a free space wavelength. Okay, so F is equal to what? A C by lambda that we know, and the guide wavelength is equal to what? A lambda by under root of 1 minus lambda by lambda 0 bracket square. Now, what do you mean by this lambda? Lambda is nothing but a signal frequency. Okay, we consider here, and this lambda 0 is called as a cutoff wavelength. So lambda 0 is equal to cutoff wavelength, and that lambda 0 is cutoff wavelength. It is depending upon that what will be the distance between the inner wall. That is about a twice of the distance between the side walls. That is about a twice of a here. Because for a given waveguide, I suppose to consider that this one is about waveguide here. Okay, so this one is about waveguide now. What will be the inner distance? That is about a here. We generally consider that a dominant mode of propagation, that is a T10 mode. For a dominant mode of propagation, for a given waveguide, cutoff wavelength when your wave signal is propagating, and that signal is a, we can say that whatever the signal is propagating through the bench or through this guide, that signal has a mode, it is a dominant mode. So in the case of a dominant mode, the cutoff wavelength lambda 0 is equal to twice of a here. And that generally we say that a cutoff wavelength lambda 0 is a twice of a means what? That is a twice of a inner distance between the side walls of the waveguide. Okay, that is about a side walls of the waveguide. Okay, so how much is the cutoff wavelength? So we just measure that. What is the dimension there? So you can measure the dimension. So already we know that a standard waveguide is used in a microwave bench that is operating in the X band. So A is about 2.84854 centimeter. Okay, likewise. That is about a dimension. That is about a inner dimension. And then here we need to find a guide wavelength. Okay, to find the guide wavelength, then what happen? Whatever the bench we have, this one is about a micro bench. Micro bench consists of what? Source supply, the source, isolator, flap attenuator, frequency meter, standing wave detector, then a short. Okay, so then a short, and then standing wave detector, that tunable probe is connected to the VSWR meter. And one end of a standing wave detector, input from the frequency meter, and output of the standing wave detector, another end, is connected with a short. And a tunable probe is connected to the VSWR meter. Now, to find the guide wavelength here, we need to terminate that the micro bench with a short. So this one is the means one end of a standing wave detector is connected to the short there. And then when we consider connect the short here, so then in that case, because of a standing wave detector, the standing wave pattern in the uh, standing wave detector is generated because of that a short. So in that case, here standing wave detector is nothing but a slotted section. In the given particular slotted section, the standing waves are generated because of a given short. And then we need to measure here through that particular pattern, okay, whatever the standing wave here. So we need to measure that what will be the VSWR there. Okay, so we consider that output of this tunable probe of a standing wave detector is connected to the VSWR meter. And then we need to find out the distance between the two minima. Okay, so on the VSWR meter here, we supposed to consider that standing wave detector tunable probe is connected to the VSWR meter, and then on a VSWR meter, we supposed to find out that a two minima here. So how to find out the two minima? So we supposed to move that a tunable probe toward the source here, and then we need to find out a consecutive minima. Okay, and then that particular minima is used to calculate that what will be the a guide wavelength. Okay, so now what will be the a guide wavelength then? So generally that a guide wavelength, okay, is equal to what? A twice of the minimum distance. Okay, so this one on a slotted section probe carrier, there is a vernier scale. Okay, so that vernier scale is there. So we need to consider that a measure that a minimum distance. So that lambda g is equal to what? A twice of d2 minus d1. So we'll get that at two distance. One distance d1, another distance d2. Okay, so that's about whichever the maximum distance here. So we'll get that a distance there. So that lambda g is equal to what? A twice the distance between the two consecutive minima, and the directly will get the whatever the a guide wavelength there. So generally we consider that a short circuit here, and due to the short circuit short, so there will be a standing wave occur, and because of that standing wave occur, so we can connect that standing wave slotted section tunable probe here to the VSWR meter, and that VSWR meter is used to measure that a minimum distance. Okay, so minima. So where that minima is occur, and that minima is used to calculate that what will be the guide wavelength. Even we can consider that a, a maxima also. Okay, whatever the location of maxima. But what happened that vernier slotted section is a too small there. If you connect a short, so we'll get a minima there. Okay. So if you need to consider that instead of a maxima, so in that case, that maxima location will be a different. Okay, so it will be spread in this particular slot for the large distance. So that's why it is difficult to locate that where exactly the maxima occur. But we can locate that where will be the exactly minima. Okay, so that's why. So instead of using a maxima here, so we're supposed to measure that a minima using the a short there, and that distance between that a two minima is nothing but a guide wavelength. Okay, that's about a lambda. So this one is nothing but a measurement of what? A frequency. Okay, measurement of a frequency that propagating through the waveguide. That is about a guide value. Okay, so that's all about what you can say that a measurement of a frequency. We have seen today that measurement of a frequency in a using a deep method. So in a deep method, so we have seen that a wave meter, that wave meter is going to be rotate in a clockwise direction or anti-clockwise direction. So wherever we have the input signal and a resonating frequency of the cavity of a wave meter match, so we will get that across that wave meter a deep occur, and that deep is to measure on the scale on the wave meter. Okay, measure. There is a scale on the wave meter there, and the scale directly provide you the how much is the frequency there. That is about first method, deep method. So another method is about a slotted line method. In a slotted line method, so we supposed to consider that is standing wave detector here, and one end of a standing wave detector is connected to the short. One in is the input end, another end is the short here, and on this particular slotted section with the probe carry, there is a tunable probe, and that tunable probe is connected to the VSWR meter here. And then using the short, when we connect a short to the standing wave detector, we're supposed to find out a two successive minima, and that two successive minima distance, whichever we are getting, that distance between the two successive minima, twice of that particular distance is nothing but a guide value. Okay, that is about a guide value. And now here, that twice of a lambda 0 is nothing but what? A cutoff wavelength. And that A is nothing but what? Inner sides of a inner walls of a waveguide. Okay, that is about it. Well, we can say that for a given particular waveguide there, A is nothing but what? A distance between the inner walls of a inner two sides wall. Okay, inner distance between the two sides wall. And that is lambda 0 is equal to twice A. Why lambda 0? That is a cutoff wavelength. And that cutoff wavelength, when your signal is propagating through the guide, is about that signal has a that mode of that particular signal is a dominant mode. Generally, we say that any microwave bench in a practical laboratory or any laboratory that is used a dominant mode of a propagation. The dominant mode means what? A T10 mode. At a dominant mode, a cutoff wavelength is equal to twice A. A is nothing but what? A inner distance between the two sides. Inner distance between the a side wall, two side wall. So that is about a lambda 0 is equal to twice. And then lambda g is equal to what? A twice of a two minimum distance. Okay, minimum distance between the two minima. Okay, that is sorry. That is a distance between the two minima, D1 and D2. So that will get the a guide value. So that's all about a measurement of a frequency. So we have seen today a measurement of a power. We have seen a measurement of a attenuation there. So in a measurement of a attenuation, we have considered that the RF substitution method, and we have seen that another method is about a power ratio method. And in a power ratio method, we are supposed to measure the power with device under test and without device under test. And in a RF substitution method, we are supposed to measure the power using the device under test and replacing the device under test with the attenuator, variable attenuator, and then adjust that variable attenuation value with respect to how much is the power attenuated by the device. So that's all about that. A measurement of a attenuation, measurement of a frequency. Okay, that's all about the all this measurement topic. So thank you all of you. With this, we stop here. So thank you all of you.